Today's lesson is about data handling, and this is a new subtopic within the overall chance and data assessment. So we've finished looking at probability. It does pop up a little bit in the next few topics, but generally that's it for this assessment. So data handling is looking more at the statistics side of chance and data, um, and particularly today, it's based around looking at something called the PPDEC inquiry cycle. So PPDEC, quite as an acronym, quite simply describes the steps within the inquiry cycle. So there is a problem, a plan, we have data, we have analysis, then conclusion. And you'll notice in this diagram that I've shown you of the inquiry cycle is that it's a loop, so it folds back onto itself. And this sort of describes a lot of the inquiry that goes on in universities and science overall. That we try to solve problems, but when we do that, or we find information about a problem, it creates other questions that we need to find the answer to. And that generates an increase in knowledge overall. And the way the university system works is that one university, one particular person in a university might be doing one of those um, inquiry cycles, and then that creates other work for other people to look at. So they look at their results and then go, well, I wonder what that means. And we progress overall. So I'm going to illustrate a little bit how that works, particularly in terms of statistics. Um, and hopefully that gives you an idea of what the purpose is that we're trying to create. So we've got a cycle. So the first thing within it, whenever a cycle is you have an overall problem that you want to solve. So the one we're going to look at in this example is, should we have school sport? It's something that's debated quite often. A number of people complain about the amount of time school sports people are out of class. Other people advocate that it's a great way to engage people at school. They wouldn't be at school otherwise, all those sorts of things. But they're sort of anecdotal or stories about what is actually happening. With statistics and science, we need to have a bit more, be a bit more analytical about that and actually have data to back that up. So the inquiry cycle helps us generate that data to make decisions and conclusions and then move on to further steps. So from our problem, should we have school sport, we have to choose for our inquiry one particular part of that that we don't know that we want the answer to. And the thing that came to mind to me was, I wonder why we have school sport. So why is it that people actually have school sport? You can go to one person to get an answer. You could even go to two people to get to an answer. But what I'd like to do in this is try and come up with a bigger overall picture of what's going on and what are all the arguments and all the ideas. So the plan I'm going to come up with, so moving along the cycle, is I'm going to create a survey where I target people in school and that I find out and try and find their opinions. So the next thing is to go and collect that data. Then once I've collected the data, I have to analyze it. Generally, a lot of the time you are trying to present that information to people who aren't statisticians uh, or people that can look at data or decipher data for themselves. So what your job as a statistician to do is to take that data and present it in a way that can be interpreted by other people. So that's what the analysis is for. Statistics, so we want to talk about the mean, the median, and the mode, and we want to present our data in graphs and where we can see clearly trends, patterns, all those sorts of things. So once I've got my analysis, I can then come up and see what was the conclusion of my survey. And from my survey, um, the most popular reasons or the largest reasons was that for people who wanted school sport was because of student engagement and also that helps academic performance. Now, at the moment, these are just opinions. So that doesn't mean we're at the end of finding out our information of whether we should have school sport. It just tells us that that's what people's opinions are. So it leads us to the next part of the cycle, which is, well, is that true? So I've chosen one of those talking about helps academic performance, and actually, is it true that there is a difference between students who play school sport and students who don't? It's a perceived one because our survey tells us that, but we actually have to go out and see if that's the reality. So that leads us to our new inquiry cycle. So our problem for our new inquiry cycle is there a difference in the grades between students who play sport compared to those who don't? So then that creates the next part of our inquiry where we're specifically going to look at, I wonder if if year 11 students who play school sport gain more credits than those who don't. So that's our question. So it leads us to a plan. This time we're going to collect data from 2019, and then we're going to carry out something called an inference, where we take a sample and then we look at the information to predict what it means for the whole population. So once we've gone and collected that data, we then have to analyze it and use the find the statistics, present the graphs. And then once we've found those graphs and statistics, we look at those and we come to our conclusion. And after this inquiry, the conclusion that I came up was students who played sports had a higher number of credits than those who didn't, which is an interesting result. It backs up what people were saying in the previous part where we gave them a survey, that the perceived idea that students in year 11 who play sport will do better, and it turns out the data backs this up. The only problem with that, though, is it's just the data. There's too many variables. What we can't do from an inference is predict whether sport is the specific reason. It could be that there's another reason why sports players get that. It might be that they get extra support. It might be it might be another reason. So that creates the flow on to our next inquiry. So, which is looking at, is sport causing the increase? So again, we go back to our inquiry cycle. Does sport increase cause you to gain more credits? So we come up with our question we want to test for this inquiry. I wonder if playing sport for a term will affect the number of credits you gain. And our plan for this time is that we're going to carry out an experiment. Now, experiments are specifically about trying to find whether one thing causes something. You can't say that something causes something without carrying out an experiment. And what makes an experiment different from an inference is that we manipulate who plays sport, how long they play, and that we try to control the rest of the variables. So the next thing is carry out the experiment and get the data. Once you've got the data, we present it again in statistics and graphs. And the conclusions from our experiment was that we found no cause. Now, that's an interesting result because it's going through from the survey through to the inference that we did in the last inquiry. It was all looking good until we came to the experiment. So it could be that it's something else that's causing that increase in academic performance. So that leads us on to what we would flow on to next time is what has caused the difference in the year 11 NCEA results. So that part's really important. And these three inquiries have shown us that we started off with the question, should we have school sport? And we've got to the point where we're actually not sure. It was looking good in the first two inquiries. The third one sort of thrown out that it wasn't the sport that caused the reason for the difference in the year 11s, but it could be some element of sport that's related. The details of those inquiries is not particularly important. The concept I hope you take out of it is that we started off with a question and we're slowly building more and more knowledge. So we're moving up that scale. And generally, a lot of the breakthroughs that we've had with science and things like that have been as the result of not just one experiment, but a number of experiments and a number of inquiries. So this is the point of using statistics to answer questions rather than going on anecdotal evidence. So now we need to move on and look at the specifics of each of those so that you're able to follow the inquiry cycle yourself. So the first part we're going to look at is collecting data. So some key definitions that you need to understand. So first of all, the population. You might have heard me talk about the population already. The population is the bigger group. It's the group you're interested in. So for example, it might be Year 9 boys from New Zealand. It could be the people of the UK. It could be play centres in New Zealand. It could be anything. It's really important to define the population because any statistics you take or samples you take will be specific to that population. You can't or you shouldn't imply any results from a sample to another population. So any decisions you make about using a sample should be made by the population it had come from. The other thing is with a census. So a census is a great way to get a clear picture of the population. So if you survey the population and then analyze their results, it can be you get 100% accurate results. However, the issue with a census is it's quite costly and difficult to handle. In fact, the New Zealand census is well known to be unreliable because of the different issues around trying to make sure that you survey everybody. If you think the process of the New Zealand census is every 5 years, everyone in the country is given a survey that they need to fill out and put their information. Well, there's a lot of times whenever they choose it, there'll be someone overseas, there'll be visitors in New Zealand, and all those sorts of things. So it's inaccurate, but it's actually in some ways it's the best that we can use. So, and to give you an idea, is that if you actually want to do a population of all the Year 9 students in New Zealand, that there's 55,000 of them who took the Census at School survey, and there's a lot who didn't. In fact, there's about 1 million New Zealand school students. So if you think of that's divided up between 13 years, you're kind of looking about just under 100,000 for each year group. So if a census is too costly and difficult to handle, a sample is the opposite of that. So a sample is just a survey of a smaller group that represents the population, and you try to make it represent the population as best as you can. It just makes it cheaper and easier to handle, and also generally about 30 students is enough for a sample. So the plan, or what we do with the sample, is that we have to take the sample from the population, and that's what's called an inference. Now, the inference gives us an estimate of what the population looks like. It won't look exactly the same because no sample will, but you would hope that if we took an average of the sample, that'd be pretty close. Now, generally, a lot of these systems, so the perfect example is to do the census, but if you can't do that, you want to get whatever fits the information you need. So for instance, if you only need to know within the nearest meter how tall a Year 10 student is, you don't need a very representative sample at all. A mean of most samples you get will give you a good indication. However, if you wanted to work out what the average is to the nearest millimeter, you might need a more accurate sample or a more representative sample to work that out. So when you're taking a sample, there's two questions you should be worried about. Is my sample big enough? Is my sample unbiased? Now, the key thing is that word unbiased. Lots of people get confused about the difference between bias and fairness. So in statistics, bias refers to the representation of the population, not whether it was fair that someone was asked the question or not. So when you refer to bias, you should always talk it in terms of representation as well. So I've got a relatively short video here that I want to show you that goes through some of these points. I'll play it now.
To known factors. Statistical inference is the process of drawing conclusions about population parameters based on a sample taken from the population. Because of natural and explainable variation, each sample will only approximate the population. Say I took a sample of 5 students and you took a sample of 5 students from the same class and asked them about the number of texts they sent yesterday. Do you think you and I would get the same mean or average? I presume you've said no, because that is correct. Because our samples will include different people, we are unlikely to get the same mean or average. That is another kind of variation. The fact that our samples included different people is the underlying cause of sampling error or sampling variation. Because we are looking at a subset of the population, we are not getting all the information about the population. And there are almost infinite different samples we could take, each with its own distribution. The term sampling error is a bit of a problem, as the word error suggests that a mistake has been made, but this is not actually the case. Sampling error arises due to the variability that occurs by chance because a sample, rather than an entire population, is surveyed. When samples are small, the potential effect of sampling error is greater, but even with a big sample, we can never eliminate sampling error completely. Typically, a larger sample size leads to an increase in the precision of a statistic as an estimate of a population parameter. You might think that if we are really careful to take a random sample, we might avoid sampling error. But even perfectly random samples are subject to sampling error. Sampling error exists because a sample is not the complete picture of the population. You might think that if you take a larger percentage of the population, that will reduce your sampling error. But, strangely enough, unless the population is really small, what matters is the size of the sample, not the percentage of the population it represents. So, a sample of 100 from a population of 1 million is just as useful as a sample of 100 from a population of 10,000. The sample size, known as n, is what matters. The larger the sample is, the less influence sampling error will have on the information we get. We cannot generally measure the extent of sampling error. To do this, we would need to know the true population parameters such as the mean, median and standard deviation, as well as the equivalent sample statistics. And if we knew the true population parameters, we would not need to take a sample. But with probability modelling and procedures like bootstrapping, we can get a good idea of the effect of sampling error. Probability models underpin statistical tests like the t-test, chi-squared test and f-test. Confidence intervals express estimates of population parameters based on the information gained from a sample. Statistical tests generally require that the sample is random and unbiased, and with as little error as possible. There are many ways that the distribution of a sample may not represent the true distribution of the population. The other errors that may occur when a sample is used to infer about a population are categorised as non-sampling error. Examples of non-sampling error are badly worded questions and self-selection of sample members. Both of these can cause bias, which is a non-sampling error. There are many sources of non-sampling error, which we will talk about in our companion video, Bias and Non-Sampling Error.
So the key point I wanted to finish on is talking about random sampling. So random sampling is the way to avoid bias. And to be fair, random sampling is the one that it's the most common sense one that you're probably most familiar with. So what we want to make sure in any sampling method that every member of the population should have an equal chance of being selected. So the way to do it is to have a list or a sample space of the population. You allocate a number to each one of the members, and then you randomly generate numbers until you have your sample. Now, there are other random sampling methods that you can use, which you'll learn as you go further in stats. So go to your lesson page where there should be some questions that should follow.